Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. Don't need the headphones on anymore. This is all math-based, of course, and as always, it is an honor and privilege to be serving you here today, as it is every day here in my virtual classroom. I don't know why I don't just restart the video here now that I did that. I'm making a solution guide video for my Integrated Math 1 class as we are looking at exponential functions in algebra and specifically in what are called geometric sequences. This is their introduction to geometric sequences. They have used arithmetic sequences in the past. So what I'm going to do is play under the assumption that you've heard about arithmetic sequences before, understanding a list of numbers, have a specific pattern of a common difference, and you have terms and term value, because now today we're going to be talking about common ratio, and I have 10 problems for us to do. They're all pretty standard. We're not using explicit form at all right now. We are using the logic of recursion, and I want to stress the importance of getting exact numbers, specifically with fractions, when the problems are non-contextual without models, and in word problems, when there is context in a model, we will use decimals, but you still got to stay exact with it. So with that being said, I'll probably need a calculator at some point. I'll pop it up when I can. I have only about a half hour to work with before I have to open up some tutoring hours for my students here, so hopefully I get it done within that time. I know I tend to over-explain, but of course it's always to your added benefit to see that. If you have any questions besides these ones that I do, this is out of the textbook. I'm going to only do the problems that I circled for my students' problem set. If you have any other questions beyond that, put them down in the comment section below, and check out the description section for the PDF that I have here and timestamps for each problem that I do for you. With that being said, let's go ahead and get started with the first set of problems, 1 through 5 here. I'm only going to do the 1 through 5. I'm going to skip 6, 7, 8. I think I do number 10 as well in this set. But we are going to find the common ratio r for each geometric sequence and use r to find the next 3 terms. A geometric sequence is a list of numbers that have what's called a common ratio. A common ratio is a number that you multiply over and over to go from one term to the next. They call it a ratio because to find that multiplier that we're going to be using, you might have to use division to figure it out. In other words, in number 1, we have the numbers 5, 15, 45, and 135. It's clear to probably most that the number you're multiplying here is 3. And you would be correct. Now, if you're uncertain as to whether or not that's true, there are one of two ways you can figure that out. They both end up being the same thing, but whether you want to hear it one way or the other is up to you. In this book, they kind of just show and they say, hey, do 15 divided by 5 to figure that number out. And listen, this is perfect. This is what you do. 15 divided by 5, that's 3. Double check that or just do it again. 45 divided by 15, that's 3. 135 divided by 45, that's 3. Now, where do these numbers come from? They are the numbers in the list. Why did I choose the numbers the way that I did and in the order that I did? Because to figure out, here's the other way you can do it. To figure out 5 times what number is 15, you can write 5 times what number is 15, and you can solve for that number by doing it algebraically, dividing by 5. What we're doing, guys, to figure out what we're multiplying to go from one number to the next, you take the number, you take some number and divide it by the number before it. 5 times what is 15? Do 15 divided by 5 to figure it out. 15 times what is 45? You do 45 divided by 15 to figure it out. You can write it as an algebraic equation here. 45 times what is 135? You do 135 divided by 45 to figure it out. Now, you shouldn't have to test more than once because they tell you it's a geometric sequence. That means we know that with absolute certainty, there should be a common ratio. There may be potential for a typo, and you may have made a mistake, but once you do it once, it should be the same number each time. So unless they're asking you to check and see if it's a geometric sequence first before you determine the common ratio, you should only have to do this once. Now, once again, we knew that this number was 3 anyway, so to show this extra work might not be of your need. However, it might be for future problems, so I will continue to show it. So this times r each time is a times 3. My common ratio here, r equals 3. I will be multiplying by 3 each time. Now they ask us to use r to find the next 3 terms. So every term in a sequence, again, is separated by a multiplication of 3. So if I multiply 3 each time here, 3 more times from one number to the next, 135 times 3, this is where you guys might use a calculator. I know this number. This is 405. That gives you 405. And then 405 times 3 should be 1215. And 1215 times 3 is 3645. 3645. So 1215 times 3 is 3,645. I like to try and flex my mental math muscle whenever I can. Ooh, triple M. I like to flex that muscle whenever I can, but trust me, even I will be using a calculator sometimes, especially with the decimal problems. Okay, let's move on to number 2. Same thing. Find the common ratio and use it to find the next 3 terms. Now, this is what's called an oscillating geometric or an alternating geometric sequence because the signs change each time. And that's the result of when we multiply, it happens to be that we're actually multiplying by a negative value. Now, once again, it may be obvious to you what's occurring here. Just make sure you understand you are multiplying. And if you're uncertain what that is, you can set this up almost algebraically if you like. Negative 2 times some unknown r equals 6. Divide both sides by negative 2. And 6 divided by negative 2 is negative 3. So r equals negative 3. That's what we're multiplying by each time from one value to the next. And with that in mind, just understand that when you multiply by a negative, the sign will change. That's what you see here. And that's what we need to continue to do as we find the next 3 terms. So the next 3 terms here, we get to multiply 54 by negative 3. That will give us a negative value. Then we're going to multiply that number by negative 3. That'll become a positive value. I'll just leave no sign there. And then you multiply that by negative 3, and that'll once again become a negative value. So for all intents and purposes, if you're okay with me doing this, I'm going to do this more than just on this problem here, I'm going to ignore talking about negative. I'm just going to say, what's 54 times 3? What's that number times 3? Because the negatives are already in place where I need them. Okay, 54 times 3 is 162. Therefore, that number is negative 162. 162 times 3 is 486, and that'll be positive, 486. And 486 times 3, you'll have to give me a second on this one. 12, 14, 1458. So this will be negative 1458. I think that's correct. So those are the next 3 terms in the list as we continue to multiply by negative 3. All right, number 3 seems like an easier problem again. Once again, 4 times what is 20? 20 times what's 100? I can do 20 divided by 4 to figure that out. R is 20 divided by 4. That is 5. We are multiplying by 5 each time here. 5 is the common ratio. A positive 5 at that, and the numbers just get literally exponentially larger. So I keep multiplying by 5 here. 500 times 5 is 2,500. 2,500 times 5 is 12,500. I think the problem I'm going to struggle with is not the numbers, but how many zeros and how to say it. So 12,500. And 12,500 times 5, 625, 62,500? 62,500. I think that's it. I apologize if I'm not getting the right numbers. I don't know why they give me so much room. Oh, I know why they give me so much room. Here's something else that they might want you to do and what you'll probably see out of the book or other things. What they might write here next time is, and this is probably important for me to say now for the next video I potentially do. 4 is the first term. Let me find a different color. 4 is the first term, 20 is the second term, 100 is the third term, 4th, 5th, 6th, 7th. When we use when we use the explicit rule later for this stuff, or even the recursive rule, they use function notation. And what they might say is something like f of 1 equals 4. And what they're telling you is the value of the first term is 4. I input 1, I output 4. I input 2, the second term, I output 20. I input 3, I output 100. And I input 4, I output 500. I'll be using function notation on the next, if I make a next video for the next section I do, I'll be using function notation to do the explicit rules. It's almost a requirement to do in terms of plugging in the values and such. Now, I'm not literally plugging in these numbers, so to speak, but we are referencing the value of. And the way that we're working the recursive action right now is to say, hey, you know how to find the 5th term in the way that we did it? What we do is we take the 4th term, we take the value of the 4th term, and we multiply it by 5. So we took 500. F of 4 is 500. We took 500. And we multiplied it by 5. So f of 5, the value of the 5th term, therefore, is 2,500. So this is probably why they have all the space here, so you can find the next 3 terms in this way. I don't know how much work you'd actually have to show. It all depends here. But that's what we're actually doing right now. To find the next term, we're taking the term before it and applying the common ratio. And this is a syntactical way of showing exactly that. All right, let me move forward here to number 4. We are multiplying by some unknown value. I'm just going to put a times r right here and really make mention of this isn't subtraction, guys. It's not about addition, subtraction. It's about multiplication. You might notice that this is dividing by 2, and you'd be right, but that's not the common ratio. The ratio asks what we multiply by. You might know what dividing by 2 is equivalent to as far as multiplication, but if you don't, if you have trouble, Check this out. 8 times some unknown r equals 4. What is r? You divide both sides by 8. No, 4 divided by 8 is not 2. That's 8 divided by 4. 4 divided by 8, in fact, is a fraction that can reduce. I can divide top and bottom by 4 right here. 4 divided by 4 is 1. 8 divided by 4 is 2. If you got 4 out of 8 on a test, you got half your questions correct. R equals 1/2. 1/2 is what we'll be multiplying by each time here. Here's where I ask. I could be asking some people in different locations all around the world who are watching this video. I don't know who, but for my students specifically, I would ask and recommend that you leave this as a fraction. That you don't do 4 divided by 8, get 0.5, and then use the 0.5 to put things in. That's not to say that it would get you incorrect answers. At some point, it will if you're using numbers that you need to round. But it will also probably, for most people, require to use a calculator to find the next several terms on that, which I'm not saying a calculator is bad, but if you can do this practically without a calculator and use the fractions and show competence in that, I think that's good. We can guarantee ourselves exact answers this way. I think that's just another big part about it. We can streamline this. I can go really fast this way without the decimals. That being said, and I think I might have already mentioned this, when we do word problems, it's very recommended you use decimals. For the very reason that there's context now applied to a lot of word problems might have to do with money, especially in these sequence kinds of problems. When it comes to interest rates and things like that, a lot of times money may be involved. And that's not to say therefore it should be a decimal, but contextually it's better to say that I have $8.50 rather than 17 halves of a dollar. You know what I mean? But here, there's no context. So here, just exact numbers are what we're looking for. What are the next terms in the sequence? I need to multiply 1 by 1/2. You know how you do that? 1 is a numerator value. So that's 1 divided by another 1. Not because this is a 1, but because anything divided by 1 is it. And when you multiply, guys, we multiply straight across. 1 times 1 is 1. 1 times 2 is 2. So this becomes 1/2. Yes, 1 times 1/2 is 1/2. We'll go ahead and we're going to multiply that 1/2 by a 1/2. 1/2 times 1/2. Right here, we do 1 times 1/2 times 2. That would become 1/4. You kind of notice maybe what's happening here as we keep just doing fraction multiplication here. We're going to keep a 1 on top. We're doing times 1/2. There's a 1 on top, and we're doubling the bottom. Doubling the bottom does make something smaller, right? You get a larger denominator. Someone gets 1 out of 2 on a test versus 1 out of 4 versus 1 out of 8. 1 out of 2 is the highest percentage. That's 50%, 25%, 12.5%. And they have decimal equivalents, but I'm going to leave them like that. Those are the next 3 terms. You saw how we got this common ratio by division of one versus the other. Here's what I'll mention, though. Some people might not know how to reduce fractions. Some people are going to get huge numbers to start with, and they might not want to work with a big fraction. If you have a fraction that you can't reduce that's too large or that's too unobvious to do, try smaller numbers. You didn't have to do 8 times something is 4. 2 times the same number is 1. So I could have done this. 2 times r equals 1. Divide both sides by 2. And you know what you get? R equals 1/2. That one didn't even need to reduce the fraction. Or if you needed to, it's a smaller number. So pick the numbers that you want to choose. I'll be sure to keep doing the same thing as just a good practice for yourself. Okay, number 5. 72, -36, 8, -19. It looks like, once again, it's one of those ones where we're going to be alternating signs. For me, I already know here, the next term, the 5th term is going to be positive, the 6th term is going to be negative, and the 7th term is going to be positive, just as a result of the alternating sign. So even though I'm going to write the common ratio as a negative number, I'm going to kind of ignore that common ratio when it comes to all the other stuff. All right, 72 times something is -36, but those numbers might get a little large for you. Maybe you want to do smaller, like 18 and -9. 18 times that same number should be -9. So you know what I'm going to do to figure out what that is? I'm going to divide -9 by 18 to figure it out. -9 divided by 18 can reduce as a fraction. I can divide top and bottom by 9 here to reduce this. Remember, when reducing a fraction, you have to make sure that you divide by 1. 9 divided by 9 is 1. We can't change its value. This will be -1/2. The other one was +1/2. This is -1/2. 72 chopped in half is 36. Chopped in half is 8. Chopped in half is 9. Chopped in half is what? We'll figure it out. We'll use it as a fraction. -9 times -1/2. We already know it'll be positive, as I didn't write a sign. 9 times 1/2. Again, 9 is 9/1. 9 times 1 is 9, and 1 times 2 is 2. I get 9/2. Can I write an improper fraction? Of course, guys. Math these days, improper fractions are not only used all the time, they're encouraged at this point, except for a model. Again, if this was dollars, I wouldn't want to write 9/2 a dollar. I'd say $4.50. But we're not talking about dollars. We're talking about just numbers. So contextually, it is moot. I have to do 9/2 times 1/2 this time. Now, that's going to be 9/4. Okay, this is very, very close to last time. Only now the sign also alternates here. So negative 9/4 times a negative 1/2 will get a positive 9/8. Once again, the top is kind of staying the same here. The bottom's getting doubled, and the sign is changing each time. So hopefully it's making sense how you find the common ratio. If you want the exact decimal, guys, that's 4.5, 2.25, negative 2.25, and 1.125. Yes, those are in my head. I do know some of my fractions divided by 4 and 8s and stuff like that. So you can use a calculator. You can work it out. Just make sure you don't round anything early. I'll make a bigger point of that when we hit some of the word problems that might use decimals. There are more problems there. I'm going to skip them. I'm going to look at number 10 as just the last one here. 243, 162, 108, and 72. Even if you ask me off the top of my head, quick, 243 times what is 162? I couldn't tell you. I see 108 and 72 and I actually know, but the other ones I'm not certain. So yeah, hey, use smaller numbers when you can. 108 times what is 72? You got to do 72 divided by 108 to figure it out. Whether you write it as an equation first to then solve algebraically, or you understand that to multiply something to get something else, you divide by the thing before it. You can get this. Now this can reduce. If you have trouble reducing fractions, not knowing what the largest number is you can divide here, which by the way is 36. Maybe you're not sure. Maybe you're like, oh, I don't know, but I know they're both even, so I can divide them by 2. You divide them by 2 and you get 36 over 54. Maybe this number's small enough that you realize these can divide by 9, so maybe you divide it by 9 next, 9 over 9, and then you say, okay, that's 4 over 6, and then you divide them by 2 right there, and then you realize, oh, this whole thing was 2/3. So your common ratio here, R, is 2/3. We are multiplying by 2/3 each time from one value to the next. And this is a perfect example of when definitely not to use a decimal. 2 divided by 3 is 0.6 repeating. Besides the fact that you might have to type a bunch of 6s in your calculator and it might approximate to something else with a bunch of repeating decimals, you also do not want to round early in any sense. Not with the ratio, not with the numbers that you get. You might round to write in the number with the decimal, but that also causes another concern, unless, of course, it's a word problem. But, you might not want to round otherwise, so just, again, be super cautious of that. Fractions are perfect and exact, and as long as you reduce them, they'll also be simplified. Let's leave these as fractions. If they are fractions, 2/3 of 72 might not be a fraction. Let's check that out, guys. Let's do 72. I have a lot of room here, so I'm going to do this. Let's do 72 times 2/3. Now, if you learned anything about the last problems we did, we do put 72 over 1 and we multiply across. So you could do 72 times 2 and 1 times 3. 72 times 2 is 144. 144 divided by 3. Take out your calculators. Actually, hang on. It's 48. So that's 48. Now, here's the thing. You don't have to multiply 72 by 2 first if you'd like to instead divide it by 3 first. And this is a thing. And I only have about 12 minutes left, so I can't preach on forever here. But let me talk about this. 72, once this is multiplied, this all actually becomes, you can tell, this becomes one fraction. 72 is multiplying with 2, but guess what? It's also dividing by 3. 2 is also dividing by 1 here. So if you want to make your number smaller first, and because you can divide them because they're smaller, that's up to you, do that. 72 over 3 reduces to 24 over 1. So now I have 1 times 1 on bottom, which is 1, and then I have 24 times 2 on top, which is 48. My number is 48. So there are other ways to do that, and I'm going to preach that for the next couple times. You can do however you want here, whip out your calculator and do it. I want to show you a way that I encourage people to try, especially because it's pretty beneficial. You might not know 144 divided by 3 as easily as you know 72 over 3, like myself. Okay, 48. 48 times 2/3. Here we go. Same thing. 48 times 2/3. You know this is over 1, and you know what? When 1 times 3 becomes 3, you might as well leave it. But remember, 48 is also dividing by 3. You might write this, and 48 divided by 3 is, in fact, 16 over 1. And as you know, anything divided by 1 is just the top. So 16 times 2, guys, that becomes 32. So this next number is 32. 32 is 2/3 of 48. exact numbers. Even if you use the decimal equivalent of 0.6 repeating, I hope it would give you exactly those numbers instead of 31.99999, something like that. Okay, and the last one, 32 times 2/3. This one becomes a little bit of a, I'm seeing this in my head right now. If I do 32 times 2/3, the unfortunate thing with this, even if I divide it all by 3, 32 doesn't divide by 3. Unfortunately. 33 does, and 30 does, but 32 does not. Nothing can be reduced here. Unfortunately, we're dealing with the fraction portion now. 2/3 of 32 is not an integer. So we actually do 32 times 2 this time. We get 64. And 64 divided by 3, hey, if I couldn't reduce either of these then, I can't reduce it now. 64 over 3 will be my improper fraction exact answer there. You want a decimal version? That's 21.3 repeating. 21.3 repeating, if you had to round it or not. All right, 9 minutes left. I got 5 more problems to do. Those are the basic ones there. Working into word problems here, I got this number 15. You may use a calculator, and I very well may here as the numbers get larger. You may use a calculator and round your answer to the nearest tenth of a unit if necessary. Notice how they tell us this time, round to the nearest tenth. And I'm going to go with their decimal basis. I kind of mentioned why before. We're talking about something with physical measurements here, centimeters. I don't want to talk about 5/2 of a centimeter instead of saying 2.5 centimeters. So this time I will use a calculator, even for the decimal portion. And even though it's not going to be fully applied and realized right now, decimals are actually encouraged this time for word problems, especially when you start using things involving percentages. A common ratio can also be known as a growth or decay rate of something. And those are things, technically, we have that here, even though they're not using those words. So here we go. I just whipped up, I got my calculator out and ready here, even for you guys to see eventually. And what they show here is a ball that is dropped from a height of 900 centimeters. Honestly, the 900 is actually not even really being used in this problem. I'm really kind of surprised they use this number here because it doesn't follow this trend, I can already tell. The table shows the height of each bounce. The heights form a geometric sequence. How high does the ball bounce on the 5th bounce? So this is a list of numbers, whether it's written in a table or otherwise. This is the first number, this is the second number, this is the third number. What's basically happening here, guys, is a ball, and I'm just gonna, this is as time goes on here, but a ball's dropped from 900 and it bounces and it hits 800 feet right here, 800 in height. And then it hits the ground, bounces up again, and then it hits 560, and then it goes up to 392. This has what's called a rebound ratio, and when they said it forms a geometric sequence, that means it's going up a certain fraction, a specific, each time, a certain percentage, I should say, of the previous amount. Maybe it's 50% of the previous amount, which it's not, because otherwise it would go from 800 to 400 to 200. It would do half of it. But that's the idea. It goes up a certain percentage of the previous amount. And physically, that's kind of technically what the ball kind of really does do. So what is that number that we can multiply by to go from one to the next? Let's still figure it out the same way through division, only this time I'm going to use a calculator. I'll use the decimal. I don't think they're going to give us numbers to round, so let's figure this thing out here. 560 over 800. I divide those two, guys. I'll show you my calculator here. I won't show you each time, but just to show you 560 divided by 800. And that number is 0.7. And I assumed as much. 56 over 80 is also 7/10, it's 0.7. So this is 0.7 right here. I'm going to use that exact 0.7 number right there. And I'm going to use that one to multiply and get some of my future values here. So 0.7 is my common ratio. I need to find the 5th bounce. This is the first bounce, second bounce, third bounce. I need the 4th bounce to find the 5th bounce here. So this is my golden ticket right here. So I need to multiply 392 by 0.7. So to go to the calculator here, I have 392 times 0.7, and I'm going to get 274.4. Remember, these numbers are in centimeters. For the sake of time, I'm going to go ahead and continue on this screen. I'm going to multiply this number by 0.7 as well, and we get 192.08. Now, they say that we may round to the nearest tenth. I'm going to do two things here. Well, I'll talk about something that's in excess to this problem. I'm also going to show you the 6th bounce as well. I'm going to write 192.1 because they said that we may round. So the answer is 192.1 centimeters. However, even if they allowed us to round to the nearest tenth when we write information in a list or in a table, you may not use the rounded value to find the next one. If I wanted to find the 6th bounce, for any reason, I know it's not a part of the problem, but this probably goes in the next problem. If I wanted to find that, I cannot take 192 to 192.1 to multiply by 0.7. Okay, just compare this number to the actual one. The actual number was 192.0, I think 0.08. Multiply that by 0.7. Even though this isn't a massive difference, this is only a difference of 1/100th of a centimeter, there is a difference. And it's important because there's a difference in the next one. Sorry. There's a difference even in the next number as well. What about the 7th bounce, 8th bounce, 9th bounce, 10th bounce? In proportionality such as this, when we multiply over and over, I guess it's not proportionality, but there's a different word I'm thinking of. In this kind of context, these numbers start to drastically change more and more over time. So do not round early when it comes to making a future calculation. There is a difference between these values, especially if you were thinking about something like money. There's a difference between 45 cents and 47 cents. It's 2 cents. That's not much to you, but there is a difference. And we're going to make sure that we adhere to those things. Now, rounding-wise, just to be approximate here, 192.1 is fine. Just make sure if you find another number, you use the exact 192.08 instead of something different. What's likely going to happen here, guys, only about 4 more minutes left I can stay in here. I'll just pause the video and come back. You won't know the difference, other than I might be sweatier and more tired because the day goes on. But I'm just going to continue. I'm going to continue until that time goes out, and then I'll pause and come back if I have to. Okay, Leo's bank balances at the... I have 3 more problems. Leo's bank balances at the end of months 1, 2, and 3 are $1,500, $1,530. I'll definitely have to pause and come back. And $1,560.60. The balances form a geometric sequence. What will Leo's balance be after 9 months? So this is month 3. So we need 4, 5, 6, 7. Running out of room. I don't know if these numbers will get much bigger or anything like that. It's only going up by about $30 each time. 8 and 9. Actually, what I said is important to talk about here. It doesn't go up by $30 each time. Notice it went $30 and then it went $30.60. Ooh, much different. But the thing is, this difference will grow more over time. There's going to be a stark difference between just adding 38 times from month 1 to month 9 and multiplying by something a couple times from there. You're going to make more money this way because of the way that the interest rate is growing. That's how this geometric sequence works. So let's find out that common ratio. I'm just going to use 1530 over 1500. I think it's 0.02 because 30 1500s, 350ths is, yeah. So let's check that out. 1.02 I should say, because it's going to be more. 1530 over 1500, that's going to be 1.02. So our common ratio of 1.02 is what we're going to be multiplying by each time here. And remember, this is money. So I'm going to be rounding each thing to 2 decimal places when I write them down. However, I'm going to be using the exact number they have in the calculator in order to get the next one. So I'm going to stay on the calculator screen while I write these things down and come up with them. And you're going to just kind of see that difference there. So we're going to multiply this by 1.02 each time. I don't know if I should, I'm not going to write this each time right here, but by 1.02 recursively from one value to the next. Okay. Listen, they didn't require you to write all these things down. I'm just going to do it for the sake of talking about the rounding versus not. Okay. So here we go. In the graphing calculator, I'm going to start with $1,560.60 and multiply that by 1.02. And I get, my face. And I get my face. And I get 1591.812. Now, there's something else I would probably say on rounding here, which is you shouldn't round up. I don't know if I have the luxury of time to talk about that right now. I'll make sure to get that part of the conversation in. I'm going to run out of time, so I'm probably going to pause this video. But I'll probably get the part of the conversation in why we shouldn't round up. It's really quick talk when I resume back. But let me do one more. But the point is, when I do one more, guys, I'm going to multiply the previous answer by 1.02. I'm not going to take 81 cents. I'm going to take 81.2 cents. The fraction of the penny is involved in finding the next one. Even if I cut off the answer by a couple decimal points here, I will be using this exact number to find the next one. And I hope that makes sense. Okay, I'm going to leave it there for a second. This video, you're not going to know about the pause. I'm just going to pause it. I'll come back later after I do my 2 hours of tutoring. Thank you. Okay, welcome back to the channel, guys, where it's all fun and games until you got to do geometric sequences. Sorry, I did a couple hours of tutoring. I had another meeting that was, I'm done. I'm taken care of. I'm going to continue on. Ooh, I got to find this thing. Hang on, because when I was tutoring, I was working on something completely different. So, sorry that I just unpaused this unprompted. Let me go ahead and think about where this file is. Uh-oh. I should pause this again in a second. 14.1 solution guide. Let's fire her up. Okay, guys, I'm back. Let's see if this pops up. Perfect. Okay, so where we last left off, I'm not sure. Does my calculator still have the old things? Yes, it does. So what we last looked at here was I was doing a calculation multiplying these numbers in, and I said that I would multiply them in and I would write them down meanwhile. So what I'm going to do is I'm going to continually just be multiplying by 1.02. And honestly, if I just hit the enter button, it would show the future numbers after. So if I enter again on my calculator, it's going to do times another 1.02. What 1.02 means, even though it doesn't have to do with what we're talking about yet, is it's a 2% increase in something. So a 2% increase from 1656 is 1689-ish, right? Not like the increase that GameStop and AMC are getting right now after hours. Oh my gosh, they're going to the moon. Okay. Yeah, the question is, do I want $100,000 or $1 million or $6 million? Oh, let's go to the moon. All right. I'm going to start writing these numbers with only 2 decimal places here. So I'm going to write I know you can't see me writing this, but I'm going to write 1656.12, and I'm going to write 1689.24. Now, before this other one goes away, actually some other ones might pop up. I have 2 more to write in, so I'm going to do, this is fine. This is perfect. Okay, 1723.02, and lastly, 1757.48. Okay, so a couple things are at play here. First of all, you are probably not required to write all the numbers, write every single one of these numbers leading up to this. You were probably only trying to find this last number here, which is which is $1,757.48. That would be 9 months in, because this is month 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's 9 months in. So that's the first thing. You probably weren't required to write all the numbers leading up to it. But I wanted to write these for 2 different reasons. Number 1, to talk about when I round, and I'm quoting that because I'm not really rounding, but when I round, how I do it. When I truncate, how about that? When I remove decimals, how I do it. And number 2, the fact that I did not round numbers leading up to this. Okay, I did not round numbers leading up to this. So, I didn't use 0.81. I used 0.812 because that was the number that was in there. When you look back at my graphing calculator here, you see the 1723.028501. I didn't just use 1723.02. Those fractions of a penny are being used in the future calculation. Even if they don't exist here in my numbers, that fraction of a penny still exists in my calculation. And before you say that you don't think that's very important, a fraction of a penny, if you compound this amount of percentage over a long period of time, it absolutely matters. My own students know how much 1 single cent can take you. If you double that amount after 30 days, it'll take you up to the moon. It'll take you up to past $5 million. Yes, it matters. It absolutely matters. And you don't want to cheapen somebody from that. So that's why, even though I didn't use these numbers in a rounding fashion, even though those numbers aren't included in my dollar figures, they are still used in my calculations. Okay? They're still used in my calculations. That being said, I did not round. You might notice this number says 1723.02. When you go back to the calculator, you'll see that this thing says 1723.028. What most people will tell you is when you have a number that's greater than 5, that's 5 or more right here, you round this up to 0.03. I'd understand if this was a non-contextual problem and we were approximating. However, and this can be argued either way, you'll see websites mostly go in favor of what I'm about to say here. Because we're talking about limitation of something and money, the real question is, did I actually reach the 3rd cent yet? Did I actually reach $1,723.03? The answer is no, I did not reach that. I'm at fractions of a penny leading up to it, but I did not actually get that 3rd cent yet. Or just like here, I did not actually get the 49th cent. It's really close. I'm about to. Probably a couple days from now, I'll get that 49th cent, whatever it is, but I didn't actually get it yet. Okay? Consider this. Consider that, and I'm going to be done talking after this about this problem. Consider that you were trying to touch a basketball rim, and a basketball rim is exactly 10 feet off the ground. If you jump with a reach of 9.99 feet off the ground, are you touching the basketball rim? No. You're close. You might as well be. Maybe a fingernail can scrape it, but assuming that the reach is the maximum height that your follicles can actually breach. If it's exactly 10 feet in the air and you're 9.99 feet reach, you did not touch the rim. You can't just round it up and say, yeah, I touched it when you didn't. And I think that's my best way of saying it. You did not touch the rim. We did not reach the 49th cent. So anyway, that's all I wanted to say on that. So I'm not using the rounded. I'm not multiplying this by 1.02. I multiplied 0.812 by 1.02 and whatever number that is. So use your calculator in the exact numbers that are inside there. That's why I'm just doing the times this, times this, times this. And guys, what we're doing right now is a recursive pattern right here, where this takes a longer time to do to write these down. We'll find a fast way to do this at another time, so that even I could find, what is this, months? I could find month number 80 on the spot. Just type in an 80 and let it go, and we're going to do that in another solution guide video. This right now is just practice of recursion, all the stuff I said. Okay, I'm going to go ahead and move forward here. Let's go ahead and look at number, what do I've circled next? Two more problems, number 20 and number 21. And I'll be fast on 20 to make amends for you guys here, especially because we've actually seen this sequence before. A turtle population grows in a manner that can be represented by a geometric sequence. Given the table of values, determine the turtle population after 6 years. So we have year 1, 2, 3. We need 4, 5, 6 right here. We got to determine the common ratio. In this case, it's a simple times 3. We already talked about this. In fact, we talked about it so much, guys. If I go back a couple pages here, see that sequence? Times 3 starting from 5. This would be month, or I don't know if this was month, it was years. Year 1, 2, 3, 4, 5, 6. I'm not going to spend a long time on this. If you already have work for the answer, why not just take that answer? There will be 1,215 turtles. I don't know what these turtles are doing on this island. Man. Wait, was this an island? Just a population. I don't know what these turtles are doing to reproduce so fast, man. It must be genetically modified. But yeah, this was what? 135, 405, 1, 2, 1, 5. In the end, it's a word problem, so we got to say turtles. You might have seen that I showed the dollar value on this last problem here. Dollars. Use your units, and obviously there are decimals when it comes to money for the cents there. But use your units there, and I say 1,215 turtles after 6 years. All right, number 21. This is the last one here. Consider the geometric sequence, -8, 16, -32. Select all that apply. All right, the common ratio is 2. So it's basically, is this true or false? A, is A true or false? Is B true or false? So the common ratio is 2. Well, there's something along those lines there. -8 times 2 is -16, but when it's a +16, it looks like that number is going to be a -2. So is R +2? No, it's -2. This is, I don't know if they want us to write true or false. It says select all that apply, so I'm going to, no. The common ratio is -2. It's even better when it's false, correct what they say, right? I like doing that. Otherwise, you could just luck out. The fifth term of the sequence is -128. Well, let's go and continue the sequence. Let's take a look at that. -8. It's only two terms away. Need to find the fourth term to find the fifth term. Now that I have the common ratio is -2, good thing I have it. -32 times -2 is a +64, and 64 times -2 appears to be indeed -128. That is true. That is true. I'll go and circle that as a selection. Yes, sir. Part C, the seventh term is 4 times the fifth term. This one's interesting because you can come up with this in more than one way. Some people might multiply until they get to the seventh term, figure out what it is, and compare them. You can totally do that. I want to show you something else kind of different here. I'm not going to use these numbers. I'm just going to use the idea of recursion. Here's the fifth term. Even though, look, listen, we know what the number is, but right now I'm going to say who cares. Here's the fifth term. It's some number. Here's the sixth term. Here's the seventh term. What are we going to do to go from the fifth term to the seventh term? We're going to multiply the fifth term by -2, and then we're going to multiply the sixth term by -2. Basically, what we're going to do is we're going to multiply by -2 twice. We're going to do times -2. We're going to do some number, some unknown number, times -2 times -2. -2 times -2 is +4. That becomes 4 times x. You know what x was? The fifth term. You know what the seventh term is? It's 4 times larger than the fifth term. I don't know if I had to put the x part, but the point was, didn't matter what this was, -128 or otherwise. We're multiplying by -2 and by -2. We're multiplying by 4. The answer's true. whether or not you come up with that number. Now, 128 times 4 is 512. So there's negative 512. That's 4 times larger. This is 256 in between. That, you can also get that and just divide and figure out that's 4. But you don't actually need the numbers to know that information. All right, the 8th term is 1024. Well, now it kind of does sound like I should use that 7th term here, so I'm glad I have it. So the 8th term here, I'm going to go and multiply that by a negative 2 right there as well. And 1024, yeah, times negative 2. I don't know if you guys know your powers of 2. It took me a second to determine where I was at. This is indeed positive 1024. Hang on, so this was true. I don't know if I'm supposed to put true or not. This was true. This is true. You know what else you could do? Let's say you didn't get these numbers. Come get to the notion of what we just did for the last one, 4 times the 5th term. The 8th term is how many times more than the 5th term after that? We'll do times negative 2, times negative 2, times negative 2. Multiply those, that's times negative 8 when you do the whole thing. So you can do negative 128 times negative 8 without getting all the other numbers, and you get 1024. This is a bit of a key into what you, not exactly, but this is kind of a bit of a key into what you'd be doing to save yourself from multiplying each time. Multiply once in terms of what that number is. Dive into that at another time. And the last question here, the 10th term is greater than the 9th term. So if you think about this as we're doubling each time, well then no duh it would be greater than the 9th term because it'll be double the 9th term. However, we're not just doubling, we're multiplying by negative. So the real question at play, all I need to ask myself is the 10th term positive when the 9th term's negative, or is the 10th term negative when the 9th term's positive? Because it doesn't matter if it's a massive negative number, a negative is always smaller than a positive. So just looking at the list right here, not the actual numbers, but their signs, I'm just going to do this and just kind of show you that you don't always have to actually calculate, even though I'm only 2 steps away. The very first term was negative. That's an odd number. The first term was negative. The second term is positive, and alternate. So every odd number is negative. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every odd number is negative. Every odd term is negative. Every even term is positive. This is the 9th term. This is the 10th term. The 10th term is positive. A positive is greater than a negative. 10th term is positive. 10th term is greater. Therefore, it is true. So the only one that seemed to be false was the first one. It wasn't a positive 2. It was a negative 2. And that seemed to show up. All right, I had fun with that one. Because I had time left over, I'm glad I was able to cover that with you guys. I sure hope that you enjoyed this too. Sorry for it being kind of a bit of a longer video. But that'll do it for me. Ask yourself the questions in the comment section down below if you have any. And take care. This is Mr. Robinson. I did that backwards. This is Mr. Robinson. Take care.